Hi folks, today we're going to talk about the Z-transform, which is the transform we use to analyze discrete time systems. In a way, you can think of it as the analog to the Laplace transform for the continuous time system. So things will work pretty much the same way, properties will work pretty much the same way, but this is for discrete time systems. Now there's a couple of ways to develop the Z-transform, and I have put both of them in the write-up, but I'll show you right now, I'll show you the more standard way of developing the Z-transform. So here's the general idea. Now remember, we started out with the sampled function when we're talking about the discrete time Fourier transform, and that was equal to x of t times, the way we modeled it was, this was minus infinity to infinity of delta of t minus n cap t. And when we took the Fourier transform of this, we could take the Fourier transform up. We could put x of t in here, and we could write this as x of t summation delta of t minus n cap t, and that's equal to integral from minus infinity to infinity of this whole thing, right? This summation x of t delta of t minus n cap t, and then we multiply that with e to the minus j omega t and take the integral with respect to t. Or we could take the summation outside, and so we get summation n equals minus infinity to infinity integral of, let's put the delta here, and the rest is x of t e to the minus j omega t dt, right? And then we use the shifting property of the delta function, which says that the integral of this whole thing with respect to t is simply this thing with t replaced by n cap t. So this becomes summation n equals minus infinity to infinity of x of n cap t e to the minus j omega n cap t. Right, so this was the discrete time Fourier transform when we took cap t and we basically normalized it to 1. And if we do that, then we get this thing x of e to the j omega is equal to summation x of n e to the minus j omega n. Right, so this is the discrete time Fourier transform. And remember that because the sample in the case of the time function, we've sampled it, and when you sample something in one domain, you get replicas in the other domain. So x of e to the j omega is going to be periodic. So if the original x of omega looked like this, then x of e to the j omega will get replicas. And the replicas will occur because we normalized cap t to 1, so and the sampling frequency then becomes 2 pi over cap t, so the replicas will occur every 2 pi. Right, so this is x of e to the j omega. This is the discrete time Fourier transform. Now this Fourier transform, that's wonderful. That means that we can take care of discrete time sequences. But this transform only exists when this sequence x of n is absolutely summable. That is, as long as this is true. Well, let me rephrase that. If this condition is satisfied, then we know that the discrete time Fourier transform exists. Okay, but what if this condition is not satisfied? Well, we can do what we did before. We can say, well, if I have an x of n that is, say, growing, and therefore when I take the summation of it, it'll break this bound and the summation will go to infinity. What I can do is I can multiply it with something that is, say, exponentially decreasing. And then I can take the Fourier transform of that. That's what we did when we went from the Fourier transform to the Laplace transform. And that's kind of what we're going to do here as well. So instead of x of n, let's suppose I take the discrete time Fourier transform of x of n times r to the power minus n. Right? So, and r to the power minus n may be something like this, where now the product of these two, I can find the discrete time Fourier transform of the product of these two. And if I do that, then I would end up with a summation n equals minus infinity to infinity, x of n, r to the power minus n, e to the minus j omega n, right? So this now, for certain values of r, this transform will exist. The question is, what are the values of r for which this transform exists? Why do we want to do that? Well, remember that this condition here is if x was the impulse response of a system, then this condition here means that the system is stable. So basically what we have is we can find the discrete time Fourier transform anytime the impulse response of our system is, or our system is stable so that the impulse response satisfies this condition, right? What if our system is not stable? If our system is not stable, then we have to do something like this, where we find a way of finding the discrete time Fourier transform for certain values of r, and those values of r will be our region of convergence. Okay, so here's what we can do once we have this. We can do a slight, rewriting of these variables. Let me define z to be equal to r e to the j omega. If I do this, then I can rewrite the summation as x of n, and this thing is r e to the j omega to the power minus n. So this becomes z to the power minus n. N goes from minus infinity to infinity. And because now my variables are n and z, and I'm summing over n, so n will disappear when I'm done with the summation, the only variable left is z, so this thing is x of z. Right? And this transform is called the z transform. Okay, and remember that this will only be valid for certain values of r. So it'll be valid for r within some region of convergence. Okay. What does that mean for r to be within a region of convergence? Well, we'll talk a lot about that later, but for the moment, let's just make sure that we understand that r is simply the magnitude of z. So what we have is r element of a region of convergence is the same as saying z is an element of the region of convergence, right? Because z equals r e to the j omega is simply a point in the complex plane, and this distance here is r. The magnitude of that point is r, and the angle is omega. Okay. So say this is the real part of z, and this is the imaginary part of z. And a point z, which is equal to r e to the j omega, is simply something which is at a distance r from the origin and at an angle of omega. Okay, so when we say that r is a part of the region of convergence, what we mean is that the magnitude of z takes on a value that allows for this summation here to be absolutely summable. Okay, this will become a little bit more clear as we go along. So basically, this is the z transform. Okay, and the way we're going to handle the z transform is, now that we have it here, we're just going to do a bunch of examples, and so that we understand what the Z transform is, then we'll look at the behavior. We'll treat this as an impulse response. So this will become a transfer function for a discrete time system, and then we'll look at the behavior of that discrete time system under different conditions. Okay, we'll do a kind of transfer function for this thing. Okay, so let's do some examples. Okay, the way we handle the Z transform is really, really similar to the way we did with the Laplace transform. Right? With the Laplace transform, we had some standard. What did we have? We said if we had e to the minus at u of t, and we found the Laplace transform of that to be 1 over s plus a, and the region of convergence was sigma greater than minus a, and so on. Right? And then we had e to the at with a different Laplace transform and a different region of convergence. Okay, we'll do the same thing here as well. So let's take our first sequence, which is x of n is sum a to the n u of n. So a can be greater than 1, it can be less than 1, it can be positive, it can be negative, but it's real for the for now. I'm sorry, let me take that back. A can be complex. It's just some quantity. Okay, and now let's look at what x of z is. So x of z is equal to summation n equals minus infinity to infinity a to the power n u of n, that's x of n, multiplied by z to the minus n. And because I have this u of n here, the lower limit will go to 0. So that's n equals 0 to infinity a to the n z to the minus n. Or I can write that as a geometric sum. I can take that to be n equals 0 to infinity a z to the minus 1 to the power n. Okay. This is just our standard geometric sum, and therefore we can use the geometric sum formula, which is that we have this quantity here to the power of the lower limit, az to the minus 1 to the power of the lower limit, which is 0, minus az to the minus 1 to the power of the upper limit, which goes to infinity, over 1 minus az to the minus 1. Now, what we want to do is this quantity here will either go to infinity or it'll go to 0. And the region of convergence are those values of a for which this quantity, those values of z for which this quantity will go to 0. So this quantity will go to 0 as long as the magnitude of this whole thing is less than 1. So this is going to be something which is not infinity as long as the magnitude of a z to the minus 1 is less than 1. Okay, so that's equal to 1 minus 0 over 1 minus a z to the minus 1, and I have a z to the minus 1 is less than 1, or that is the same as saying a over z is less than 1. Right? Which means magnitude of z is greater than the magnitude of a. Okay. So our region of convergence are all those values of z for which the magnitude is greater than a. Remember, the magnitude is the distance of that complex point from the origin, right? So here is my complex point here in the complex plane. This distance is the magnitude, is r. Right? When I say the distance from the origin is greater than a, what I mean is that there is a circle of radius magnitude a, and my region of convergence is outside of that circle. This is important. I want you to know this one. Okay? So when we say that the region of convergence is greater than a, what we mean is that there is a circle of radius absolute value of a, or magnitude of a, and the region of convergence are all those values of z that lie outside of this circle. Okay, so that's my, so if I have, here's my first pair. If I have x of n is equal to a to the n u of n, then x of z is equal to 1 over 1 minus a z to the minus 1 for magnitude of z greater than a. Sorry, magnitude of a. I could also, if I wanted to, I could also write this as multiply top and bottom by z, and this becomes z over z minus a. Again, magnitude of z being greater than magnitude of a. Okay? You can see here that if you're thinking back in terms of the Laplace transform, the zero of the system is at z equals 0. There is a single pole in the system, and that pole is at a, whatever a happens to be. And the boundary of the region of convergence is determined by the pole, just as in the case of the Laplace transform. Okay. So that's one. Another one, the counterpart, kind of the anti-causal sequence is x of n is equal to a to the n u of minus n minus 1. Right, this is a left-sided sequence. So again, z transform is equal to summation a to the n u of minus n minus 1, z to the minus n, and going from minus infinity to infinity. U of minus n minus 1 means that the upper limit now is minus 1, so this is going to be summation n equals minus infinity to minus 1, a to the n, z to the minus n. Okay. I like to use positive limits when I have something like this. So what I can do is I can replace n with minus n, and then my limits will go from 1 to infinity instead of going from minus infinity to minus 1. So that's what I'm going to do. So this is equal to the summation, and I'll just replace n with minus n. A to the minus n, z to the minus minus n will just be z to the n, and n goes from 1 to infinity. And now I can use my geometric sum, or I can write this as summation n equals 1 to infinity a to the minus 1 z to the power n. And now I can use my geometric sum formula. So this will be a to the minus 1 z to the power of the lower limit, which is 1, minus a to the minus 1 z to the power upper limit plus 1, which goes to infinity, over 1 minus a to the minus 1 z. Right? So this thing now will either diverge or converge. It will converge when the magnitude of this quantity is less than 1. So the magnitude of a to the minus 1 z is less than 1 will be our region of convergence. Okay, and if in that case this will be a to the minus 1 z over 1 minus a to the minus 1 z, and the region of convergence is a to the minus 1 z less than 1. A to the minus 1 is the same as 1 over a, so this is magnitude of z over a less than 1, or magnitude of z is less than the magnitude of a. Okay, I can simplify this. Multiply top and bottom by a, so this becomes z over a minus z, which is minus z over z minus a, and the region of convergence now is z less than a. So if a is some point in the complex plane, notice again, my pole is at a, and if a is some quantity in the complex plane, I take the magnitude of that, draw a circle, and now the region of convergence is all values of z inside of that circle. Okay, so in the case of the causal system, I had z transform z over z minus a, and the region of convergence was outside of the circle. And in the case of the anti-causal signal, which is a left-sided signal, the region of convergence is inside some circle. Okay, now, that is important. Remember that. So let's write it. Right-sided sequence ROC is magnitude of z greater than something, some number, and left-sided sequence ROC is magnitude of z less than something. Okay, so z greater than some quantity is the same as in the Laplace case. When we had a right-sided sequence, we had a region of convergence which was to the right of a boundary, and a left-sided sequence was to the left of a boundary. In this case, when you have a right-sided sequence, the region of convergence is outside of a circle, and when you have a left-sided sequence, the region of convergence is inside of a circle. So the right side maps to outside of a circle, the left side maps to inside of a circle. Okay, this is something you will see over and over and over again. Okay, so we got these two. So now let's do some examples. Let's take a simple one first. Let's suppose x of n is equal to 0.9 to the n u of n. Right? So remember, here were our template z transform. If x of n is equal to a to the n u of n, then x of z was equal to z over z minus a, magnitude of z greater than a, the region of convergence. If x of n was equal to a to the n u of minus n minus 1, then x of z was equal to minus z over z minus a, and the region of convergence was magnitude of z less than magnitude of a. Right, so those are our templates, and if I fit that into here, I can go through and actually do all of the calculations, but I can just as easily just write this. This is equal to z over z minus 0.9, and the region of convergence is greater than 0.9. So I have a circle of radius 0.9. This is z equals 0.9 is where my pole is. So that's where my pole is, and I have a 0 at z equals 0. And my region of convergence is outside of the boundary determined by the pole. Okay. Notice something. Remember, we had initially the reason we did all of this stuff, we moved into this domain, was because when we took the discrete time Fourier transform, we needed the summation x of n, the summation of the absolute value of x of n, to be less than infinity. Well, in this case, x of n is equal to 0.9 to the n. If I take the summation of 0.9 to the n, I'll get 10, I think is what I'll get, but it'll be some quantity less than infinity. So I could have found the Fourier transform for this. Well, I can still find the Fourier transform, because remember what we did when we went to the z transform, we said we're going to take x of n and we're going to multiply it with r to the minus n, e to the minus j omega n. Okay, so in order to go from here, this is our z transform, to here, all I have to do is set r to be equal to 1, and I'll get the discrete time Fourier transform. To set r equals 1 means r equals 1 is the circle of radius 1 in the z-plane. Okay, and you'll notice that in this particular case, the radius of circle 1, the circle of radius 1 is in the region of convergence. So as long as this is in the region of convergence, I can set r to be equal to 1, and I can get the discrete time Fourier transform from it. Okay, and remember that in order to get the discrete time Fourier transform, if I could get the discrete time Fourier transform, the system was stable. So if the unit circle is in the region of convergence, my system will be stable. Okay, and we'll hammer on this a bit later on. Okay, so I can take different values for 0.9 for this, and I can get pretty much, if I made this 1.1 to the power n, then I would have gotten, let's say, x of n was equal to say 1.5 to the power n u of n. Clearly this thing diverges and goes off to infinity, so I won't have Fourier transform for it. But now notice that if this is 1 and this is 1.5, my region of convergence is outside of this circle of radius 1.5. So it doesn't include the circle of radius 1, which is where my Fourier transform exists. So I don't have a Fourier transform for this particular sequence. Okay. And like in the case of the Laplace transform, we'll look at systems which are unstable, and then we'll try to move the poles inside of the unit circle in this case, so that the region of convergence includes the unit circle and we get stability. And the way we'll do that is, of course, using feedback. Okay, let's do a slightly more complicated one. Let's suppose x of n is equal to cosine of omega naught n e of n. Right? Well, what is cosine omega naught n? You can use Euler's. So this is 1/2 e to the j omega naught n plus 1/2 e to the minus j omega naught n u of n. Okay, one of the properties we will find when we look at the properties of the z transform is the z transform is linear. That is, the z transform of a sum is the sum of the z transform as long as they all exist. So I can take the z transform of each of these individual terms, and I'll then add them up together, and I'll get the z transform of the whole thing. So let me do that. So the z transform, and I'll write the z transform like this. So the z transform of 1/2 e to the j omega naught n u of n is equal to summation n equals minus infinity to infinity 1/2 e to the j omega naught n u of n times z to the minus n. This is equal to, I'll take the 1/2 outside. So I have, and because of the unit step, the summation will start from n equals 0 to infinity e to the j omega naught n z to the minus n, which is 1/2 e to the j omega naught z to the minus 1 to the power n. Okay, I have my geometric sum formula now. So this will be 1/2 this quantity to the power 0, which is just going to be 1, minus this quantity e to the minus j omega naught z to the minus 1 and this will go to infinity over 1 minus e to the j omega naught z to the minus 1. Right. So this thing will converge when the magnitude of this quantity is less than 1. So the magnitude of e to the j omega naught z to the minus 1 has to be less than 1. And in that case, I'll get, this is 1/2 1 over 1 minus e to the j omega naught z to the minus 1. And now I have magnitude of e to the j omega naught over z has to be less than 1, right? Or we have, this is 1/2 1 over, let me multiply top and bottom by z because I'm going to do that anyway. So this will be z over z minus e to the j omega naught. And I have magnitude of z has to be, if I take this over to the other side, the magnitude of z has to be greater than the magnitude of e to the j omega naught. The magnitude of e to the j omega naught, remember e to the j omega naught is cosine omega naught plus j sine omega naught. So the magnitude of this will be cosine squared omega naught plus sine squared omega naught. Square root of that, cosine squared omega naught plus sine squared omega naught is 1. So this is just equal to 1. So the magnitude of z has to be greater than 1. Okay. Notice that we actually have the same thing, right? Instead of when we looked at a to the n u of n, x of z was z over z minus a, magnitude of z greater than the magnitude of a. That's exactly what we have. A in this case is just e to the j omega naught. Okay, so I'm just going to, instead of doing the whole thing again, for this other part of it, e to the minus j omega naught n u of n, I'm just going to use that formula now. So this will be just 1/2 z over z minus e to the minus j omega naught, and the region of convergence is z greater than the magnitude of e to the minus j omega naught. The magnitude of minus e to the minus j omega naught is also equal to 1. So the magnitude is also 1. And so now the z transform of what I actually started out with, cosine omega naught n u of n, is equal to 1/2 z over z minus e to the j omega naught plus z over z minus e to the minus j omega naught, magnitude of z greater than 1. And if we work it all out, we get, I think it was z squared plus z cosine omega naught over z squared plus 2 cosine omega naught plus 1. I think that's what it is. Magnitude of z greater than 1. Okay, so that's the z transform of this more complicated looking thing. And before we leave, I want to just go through one simple one, which is, we've been looking at things that, go forever and ever and ever. Let's look at things which are finite. And as in the case of the Laplace transform, remember the Laplace transform, when we took the Laplace transform of something which was finite over a finite interval, we ended up with its Laplace transform, which had a region of convergence, which was the entire S-plane. In the Z transform, it's a slightly different. So let's do it. Let's suppose x of n is equal to u of n minus u of n minus, let's say, 3. Okay, so that's just u of n 0, 1, and 2, right? Because we won't have 3 here. So this is x of n. And x of z is equal to summation x of n z to the minus n goes from minus infinity to infinity, but x of n is non-zero only for n equals 0, n equals 1, and n equals 2. So we get, this is just x of 0, which is 1, times z to the power minus 0, which is just 1. So it's 1, plus x of 1, which is 1, times z to the minus 1, plus x of 2, which is 1, times z to the minus 2. So that's my z transform. Now, I didn't have to do, nothing went to infinity, so I didn't have to worry about this summation converging, right? So I need to, so I didn't have to worry about any of the region of convergence stuff. So let's take a look and see, make sure that this thing actually converges everywhere. So if I take this and I multiply top and bottom by z squared, then this is equal to z squared plus z plus 1 over z squared. And you'll notice that this thing does converge for all values of z except z squared, except z equals 0. So unlike the Laplace case, where when we had something which was finite over a finite interval, the region of convergence was the entire S-plane. In the case of the z transform, if you have something which is finite over a finite interval, the region of convergence will be the entire z-plane again, but sometimes z equals 0 will not be part of the region of convergence. Okay, there's a reason for that, and we'll kind of talk about it a little bit, but later on. So the region of convergence is the entire z-plane except for z equals 0. Okay. Okay, so what have we done? We have defined the z transform to be equal to this. And the region of convergence are those values of z for which this summation converges. Okay, what we have done is we've looked at our templates, which were a to the n u of n. For this, x of z is equal to z over z minus a, magnitude of z greater than a, magnitude of a. If I took x of n to be a to the n u of minus n minus 1, x of z was equal to minus z over z minus a, magnitude of z less than magnitude of a. So a left-sided sequence will have a region of convergence inside a circle. A right-sided sequence will have a region of convergence outside of a circle. If x of n is an impulse response, then the system is stable if the region of convergence includes the unit circle, and we will look at that further on. Okay, and finally, if I have something which is finite over a finite range, all I have to do is plug it into the summation, and then I can get it without much difficulty at all, right? So if I had something, if x of n was 1 for n equals 0, 2 for n equals 1, and say minus 1 for n equals 2, if I had something like this, then if this is x of n, and let's say this is 2, this is 1, and this is minus 1, then the z transform for this would be 1 plus 2 z to the minus 1 minus 1 z to the minus 2. Right? So if I have something really simple, then just plug it into the summation and you'll get the z transform. If you have something semi-infinite, it's also, again, very simple, but you have to do the summation, right? And the idea is that if you have something which goes on forever, then try to put it into this form like we did with cosine omega naught n, and you'll be able to then apply these things again. Okay, so that's the z transform. Go to the write-up. I have more examples in the write-up. and then do the problems at the end, and you should be just fine.